Hey guys, so today we're going to be talking about some special summation formulas from pre-cal before we get back to the calculus. And if you're wondering why are we doing this stuff, well, remember last class we were approximating area using summation notation. And so before we get too far into that, I want to make sure that we remember some of these basic properties of summations. And so then we're going to do these first, and then we'll get back to the actual calculus portion later in this video, okay? So some of these are going to be formulas that you maybe remember from pre-cal. Some of them are going to be formulas you've never seen before in your life, and that is perfectly fine. Just go ahead and jot them down anyway, and hopefully they make sense. So this first one is the summation from k equals 1 to n of c. And what this means, c right here is telling me that it's just a constant, okay? So k equals 1 is my index of summation. That's where I start. I start when k is equal to 1, and I want to go to n number of terms, okay? And that's going to vary. So for example, I could have the summation k equals 1 to, let's say, 20 of 5, okay? But that means is that I am, like, every term in my summation, no matter what value of k, because notice there's not a k here, for every value in my summation, it's basically going to be a bunch of 5s. How many 5s? Well, I'm going to have 20 5s because I want to go to 20 terms. So my sum would be 5 times 20, which is 100, okay? So that's the first one. What if I had something, instead of k equals 1 of c, what if I had it of k itself? Oh, I knew that was probably going to happen. Hang on a second. Let me maybe move this down. Oh, there we go. Got it. So in this situation, if you're going from 1 to n of just k, your total sum is going to be n, which is your number of terms, times n plus 1 all over 2. So if I had k equals 1 to 20 of k, that's going to be 20 times 21 over 2, which works out to be 210. All right? If you're wondering why that works, let's think about this. Remember, up here we were adding all the terms. This one would be adding 5 plus 5 plus 5 20 times. Okay, this is adding the terms 1 plus 2 plus 3 plus 4 all the way up to 20. So essentially, you are combining all these terms together. Well, where this formula comes from, if you take your first term and your last term, 1 plus 20, well, that's 21. 2 plus the term in front of that, well, that's 19. 2 plus 19 is, 21. 3 and 18, 21. 4 and 17, 21. How many times can you do that? Well, if you have 20 terms total and you're adding 2 terms at a time, the total combinations that you would make is half the number of terms. So 20 divided by 2, so 10 times you could add up to 21. So 21 times 10 gives you 210. Okay? That's just a quick refresher of how that came to be. Another one, I don't have a good mathematical logic behind this one that won't take less than 30 seconds. So I'm just going to tell you that for k squared, you have n times n plus 1 times 2n plus 1 all over 6. Looks kind of gross, but it's really not that bad to work with. For example, if I just did k equals 1 to 3 of k squared, okay? Now, technically, since I'm only doing 3 terms, I could, if I wanted to, just say 1 squared plus 2 squared plus 3 squared. But for the sake of argument for this particular example, I'll go ahead and plug in n. So 3 plus 1, 2 times 3 plus 1, all over 6. And so then this becomes 3, 4, 7 over 6. And that reduces to 14, okay? The last one we're going to talk about today is k cubed. Let me see if I can drag this one down, move that over there, and then drag that. Okay, so k cubed, 1 to n, k cubed is n squared times n plus 1 quantity squared over 4, okay? And I have an example on the next slide, so I'm just going to go ahead and go to that. So here's what I want you to do, okay? I have 4 examples here. I'm going to put up all of the examples. Normally I go through one at a time, but you know, we're watching this via video, so that's a-okay. I want you to attempt these on your own. Okay, push pause, give it a try, and then come back and see if you get the same thing that I have. Hopefully you do. If not, well, try again. So hopefully you paused it and came back. So I have the summation from k equals 1 to 21 of 3. So I have 21 terms of 3. So 21 times 3. The summation of this would be 63. Okay. Number 2 over here, I want to go from 1 to 17 of p. Now notice I changed the letter from k to a p. That's perfectly fine. As long as this letter matches that, you are a-okay. So then remember the pattern here was n times n plus 1 over 2. So n in this case is 17. 17 plus 1 is 18 all over 2. So 17 times 9 is going to give me 153. Okay. Q squared, so from q equals 1 to 15, remember that's going to be n times n plus 1 times 2n plus 1. Oh, I don't know. I don't need to write it all out. Hang on. Let's go ahead and just put the numbers in here. So we're going to have 15 plus 1, 2 times 15 plus 1, all over 6. So 15 times 16 times 31, all over 6. So I can take out a 3 and make that a 5, and then make that a 2, and then I can take out a 1 and make that an 8. So 40 times 31 is going to be 1240, so 1240. Cool. Moving on. M cubed, I know we didn't do this on the last slide, but the example showed us that we would do n squared times n plus 1 squared all over 4. Well, in this case, it's just 1 to 6. So 6 squared times 6 plus 1 squared all over 4. So 36 times 49 over 4, basically 49 times 9 is 441. Okay, so that's a real quick recap of your summation rules. Anytime we need them for the purposes of our class, you should be able to have them handy to where you can go back and check them. If on a quiz or an exam I need you to know these, I will give you either enough hints that they are already on your paper, or you won't actually need to have them memorized, okay? So these are properties, since they're from pre-cal, these are properties you need to know and understand, but you don't necessarily have to have them memorized, although it does come in handy if you do. Okay. Other properties of sums that we want to make sure that we talk about. Okay, this first one you kind of have already seen a little bit here. Okay, we did this, where c is a constant. The sum of this is just cn. Okay. Now another property is that because c is a constant, a sub I represents some function. Okay, that you are finding the summation of. Okay. So you're plugging in 1, then 2, then 3, and then 4 up to n, and then you're adding all those terms together. Well, having this c out front is the same thing as just having the c in front of the entire thing, finding the sum of this, and then multiplying by c afterwards. Either one is perfectly fine. Like that's why they're said equal to each other. They're the same thing. Okay. Another property of summations is that you can add them together. So the sum of this function and the sum of that function is the same thing as the sum of this entire function plus the sum of this entire function as well. On the other side, you can also subtract that. Okay, so we can add them and subtract them and multiply by a constant multiple. Notice, not all 4 simple mathematical tools are there. Okay, addition and subtraction are here. Multiplication by a constant is here, but multiplying and dividing functions together, that is not a thing. Okay, and that's a pretty typical thing that for it not to be around. Like adding and subtracting, pretty basic, pretty simple. Anything else, not so much. Okay, so for example, if I had the problem, apparently it's tucked away, there it is, of 1 to 4 n squared plus n. Well, this, using this property right here, I know what the summation is of n squared. I know what the summation is of n. So I'm going to go ahead and just rewrite this. N equals 1 to 4 of n squared plus the sum from n equals 1 to 4 of n. And then I can use my summation rules that we talked about on the last couple of slides. So for n squared, my rule was n times n plus 1 times 2n plus 1 all over 6 plus, for n, it was just n times n plus 1 over 2. Okay, so we got 4 times 5 times 9 over 6 plus 4 times 5 over 2. Scroll down for a second. This becomes 4. Let's see, the 2, I can take out, make that a 2 and a 3, make that a 1, make that a 3. So 2 times 5 is 10 times 3, so 30 plus 10, I get 40. Now, for this particular problem, if I wanted to, I could have, since it's only 1 to 4, I could just say plug in the 1, plug in the 2, plug in the 3, plug in the 4, and then add all of those together. But I really want us to see if we can focus on using our summation rules. Okay. This next one, maybe. Oh, yeah. Here we go. Not on auto hide like some of these other ones. I'll have to fix that later. All right. So 2n squared minus n. So this is the same thing as 2n equals 1 to 4 of n squared minus the summation from n equals 1 to 4 of n. Well, luckily, I just did this and this one. So I can plug those numbers in from over here. So 2 times the summation of n squared from 1 to 4 was 30 minus the summation of 1 to 4, the summation of n from 1 to 4 was 10. So then 2 times 30 minus 10 gives me a total sum of 50. Okay, so these are some very basic properties of summations that you want to make sure. These you do need to have memorized, but they're also pretty straightforward. So hopefully we can keep those memorized. Okay, so now you're wondering, like, why did we do all these things? So let's get back to the actual calculus at hand. Okay, so last class we talked a lot about summations. Okay, oh, there's a little, oh, I clicked that. Okay, so how could we make our approximations more accurate than what we had? The word may have popped up a second ago, and I hope you didn't see it. But if you did see it, shh, keep it to yourself. Okay, so we did, I think we had 5. Yeah, we did 5 rectangles last time to make our approximation of our function. Okay, if I wanted to make it more accurate, well, I could do 6 rectangles, 7 rectangles, or even 10 rectangles. Okay, I could even do 100 rectangles. The more and more rectangles I do, essentially the number of rectangles is approaching infinity. So what I can do is I can actually use the concept of limits to help me find the actual, not just approximate, but the actual area under the curve. Still using the same process we started yesterday, but now taking the limit as the number of boxes approaches infinity. Okay, so we did this somewhat yesterday. I know you're like, oh my God, what is this, C sub k? Don't panic. This was an x yesterday, x sub I. All right, now it's just C sub k. It's totally fine. But basically, this general formula gives me the approximate area. Okay, if we wanted to find the actual exact area, I need to take this n right here, and I need to go basically to infinity. So to do that, I take the area. To find the area, I take the limit as n approaches infinity of this summation right here, and then that's going to give me the exact area of under the curve, of the function under the curve. Okay, so a couple of things to clear up here. Delta x we already know from yesterday, but then the C sub k, that is going to be represented by a plus k delta x, where a is going to be like on our interval. Remember how we always integrate, or not integrate, we approximate from the from A to B, okay, like on a certain window. So we're going to say, or a certain interval I should say. So A is the first number in that interval, and then plus k delta x, where k is your index of summation right here, and then delta x is this guy right here. I'm sure you're looking at this going, what is all this gibberish that she's writing down? I have absolutely no idea what is happening, but hopefully that will clear up here in the next like 20-30 seconds. If you need to pause this to write that down, go ahead. I'm going to go ahead and keep going on this video, but that's the beauty of videos. You can pause and watch and go back and do things as you need to. So the function we did last class was 5 minus x squared from 0 to 2. Okay, I want to find the exact area using the limit definition of area. Okay, to help me out here, so area is the limit as n approaches infinity of the sum from k equals 1 to n of f of c sub k delta x. Okay, and if it helps, I would write this down a couple of times. C sub k is a plus k delta x, and delta x is equal to b minus a over n. Okay, you're going to need to know all of these things to do what is coming up. All right, so my function was 5 minus x squared. This is a to b. There's my interval. So before I plug stuff into this monstrosity, I'm going to go ahead and take care of these two pieces. Okay, because there's a delta x in here, I'll go ahead and find delta x so that way I can find c sub k. So delta x is going to be b minus a over n, so 2 minus 0 over n, so 2 over n. Excellent. C sub k is a plus k delta x. A was 0, so 0 plus k times 2 over n. So then I can just make that 2k over n. Everybody okay so far? Hopefully. All right. Feeling some hesitation here. Pause it if you need to. Take a breather. Okay. Come back whenever you're ready. That's the beauty of having this on video. So my function was 5 minus x squared. Okay. So I'm trying to take the limit as n approaches infinity of the sum from k equals 1 to n, f of c sub k. Remember, this was my function. Okay, this is f of x. So where I have an x, I'm going to write c sub k instead, which our c sub k was 2k over n. So f of 2k over n times my delta x, which is 2 over n. Okay, if it helps, let me do some fancy color changing magic here. Sometimes some kids find this to be helpful. So that is this, which is not all of that. That's this guy right here. Okay, so that is what goes here, and nope, not all that. Here. Okay. And then delta x. Well, let's do blue. Blue. Oh, let's make that a little bit, there we go, easier to tell. This guy right here, same shade. Boop, 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 boop. Okay. And then this guy is that. Okay, so hopefully that helps clean that up a little bit better. Oh, it might help if I made all of that blue. There we go. All right, so this right here is the same thing as this right here. Okay, except for c sub k, I plugged in my actual c sub k. Except for delta x, I plugged in my actual delta x. Now I need to plug in my actual formula, or my actual function. Okay, so I have the limit as n approaches infinity from k equals 1 to n. My function was this, so 5 minus 2k over n squared times 2 over n. I'm going to just let that soak in for a second. Again, if it helps, let me do some color changing magic here, maybe a little bit. Boop. And boop. Eventually I'll stop doing that so that way y'all can just kind of go with it. But so now I've plugged in my c sub k into my actual function of 5 minus x squared, and I still have the delta x on the outside. Okay. Whew. So now let's see if we can somehow So now clean this up, okay? So let's go limit n approaches infinity of sum of k equals 1 to n. I'm going to distribute this 2 over, actually I'm going to go ahead and square this first. So I'm going to have 5 minus 4k squared over n squared times 2 over n. And then I can distribute this to both parts. So I've got the limit as n approaches infinity, k equals 1 to n of 10 over n minus 8k squared over n cubed. Okay, hopefully that makes sense. So far so good. So now we're gonna pull in our knowledge that we did from the beginning of class where we used our summation rules and all that stuff. So remember, our index of summation, the letter we're summing here is k. So that means anything else is considered as a constant. I want to repeat that one more time. Since k is our index of summation, everything else is considered a constant. So I've got the limit as n approaches infinity of the summation of k equals 1 to n of just 10 over n. Then I'm going to go ahead and say minus the sum from k equals 1 to n of 8k squared over n cubed. Okay, so far I've taken these two things that are being subtracted and split it up into two sums. So now I'm going to further use my summation rules here. I'm going to say that I have the limit as n equals infinity. This has no k in it, so that must mean this is a constant. So I'm going to bring it out front. K equals 1 to n of just 1, essentially, is all you have left. Okay, and then minus anything besides k is a constant. So bring it out front. So 8 over n cubed, k equals 1 to n of k squared. I am doing this because I know the property. I already know how to do this thing right here. I already know how to do that one. I know how to do this one. These are just constant multiples because anything besides anything besides k is a constant. N is just some arbitrary number that we don't know what it is, so we're treating it like a constant. Okay, so now let's go ahead and plug in those summation rules. So I've got the limit as n approaches infinity of 10 over n. Now this one is saying I'm adding 1 plus 1 plus 1 plus 1 n times. So this is just n. Okay, minus 8 over n cubed. Now the rule for k squared was to say n times n plus 1 times 2n plus 1 all over 6. Okay, remember that was the rule from the last slide. Again, if it helps. Whoa. Okay. Baby steps here. Maybe. Ha. Actually, we already used that color earlier. Let's change that up. Pink. Okay? So that is now this. Okay? And then the sum of this guy right here is now this. Okay. Is everybody following here? Okay, these two things I did using the summation rules that we had from the previous couple of slides. Okay, so now I want to clean this up a little bit and just turn this into a basic limit problem. So I've got the limit as n approaches infinity, 10 over n times n, well that just becomes 10, minus, I could multiply all that out. I'm not going to though, let's be real here. It's too much. 8n, n plus 1, 2n plus 1 over n cubed, 6n cubed. 6n cubed. Okay, so now I just have the limit as n approaches infinity of this right here. Okay, so, well, this is just, 10. All right, so 10 minus, and then now I have an infinite limit here, so I use my end behavior rules. So I've got n times 2n. The degree of the top overall, if I had multiplied it out, would be n cubed over n cubed. Oh, this one's balanced. So my end behavior asymptote is to look at my leading coefficients. So my leading coefficient on the top would be 8 times 1 times 2. So that's 16 over my coefficient on the bottom, which is just 6. So 10 minus 8/3 is going to be equal to the actual area, which is 22 over 3, or 7.333 if I round it to 3 places. So the exact area is 7.333. Now this is close to what we had yesterday. Whenever we did our right hand approximations, let me see if I can pull those up real quick. For the right hand, we had 6.48. Left hand, we had, I believe it was, oh, what was it, 8 point something? Oh, I am on the wrong, hang on, I got this. It was 8.08. My midpoint approximation turned out to be 7.36, and my trapezoid ended up being 7.28. So remember, we had said that these two right here were the more accurate ones, and then sure enough, look how close those were. Okay, so in the grand scheme of things, if we're trying to approximate area, 7.333, even though that's our exact, these two are pretty darn close. Okay, so depending on how exact we need it, this would probably cut the mustard. Okay, but if we needed to find the exact area under the curve, we would find the limit as n approaches infinity of those summations that we did yesterday. And that's how we have this lovely thing here. Okay, so this was kind of a lot to take in, fully aware. So here's what I want you to do, okay? I want you to pause the video, try this one on your own. Okay, it's a very familiar problem with us, x squared plus 1. It's a parabola. Okay, we know what it looks like. I want you to try it. I will go ahead and walk you guys through it afterwards, but I want you to see if you can do this on your own using the same process we did on the last page, okay? So hopefully you paused it and came back. And so I always start out with my formula. Limit n approaches infinity of k equals 1 to n f of c sub k delta x c sub k equals a plus k delta x, and delta x equals b minus a over n. Okay, so now I'm going to find what delta x is first. So 2 minus 0 over n, so 2 over n, c sub k is 0 plus k times 2 over n, so 2k over n. All right, so now limit as n approaches infinity. I'm going to kind of shorten the number of steps here, okay? We've already done this once. Hopefully it's starting to make a little bit more sense. I'm plugging this into my function. Okay, my function is x squared plus 1. So I've got the sum from k equals 1 to n of 2k over n squared plus 1. That's my function, okay, times delta x, which is 2 over n. If we need the color change option here, let's see. Boop. Yeah, here we go. I don't remember. Oh, that was blue earlier. So let's make that blue again. And then this was pink. And that is, nope, not all that. Just that. Pink. Okay. So c sub k plugged into my function, delta x plugged in on the end. So now let's clean this up. All right, so I'm going to go ahead and multiply that out on the inside. So 4k squared over n squared plus 1 times 2 over n. Limit n approaches infinity, k equals 1 to n. This is now going to become 8k squared over n cubed plus 2 over n. So then I have two different sums here. I'm going to go ahead and split these up and take the constant multiple out at the same time. So k squared is the only thing that's part of this sum. Everything else is a constant. So 8 over n cubed times the sum from k equals 1 to n of k squared plus 2 over n times the sum from k equals 1 to n of just 1. Okay. Again, if we need some color assistance here, so let's do, I don't want that 3 in there, like that, green, and this one is going to be orange. There we go. Okay, so limit n approaches infinity of 8 over n cubed. Now k squared, I'll go ahead and write this in green, is the sum of n times n plus 1 times 2n plus 1 all over 6 plus 2 over n. And then the sum of 1 from 1 to n is just n. Okay? So now we clean this up some more, because now we just have a basic limit problem. So 8n plus 1, 2n plus 1 over 6n cubed plus 2. And so now this becomes similar to the last time. We had a balance situation here. So this is going to be 16 over n plus, not over n, sorry, 16 over 6 plus 2. So that's going to be 8/3 plus 2. So my area is exactly 14/3. Okay, there is one more example on this set of notes. I'm going to pause the video so that way you guys can work it on your own. I'm just going to put the answer up here afterwards, and then yeah, I'm not going to have the full-fledged, I'm not going to work it all the way through because I think you can handle that. So that's two different ones. The next one should be a little bit more straightforward, but I'll let you guys work that one. Okay, so now the filled-in version of this is going to be on Canvas, but you should get an area of exactly 60. So then my next thing is, how could we have checked that graphically? Well, this is the function 3x minus 2. If I were to look at this, let's graph this. So -2 and then up 1, 2, 3 over 1. It looks like this right here. Okay, but I only want the area from 1 to 7. Okay, well, that creates a trapezoid. Okay, so the area from 1 to 7, I could check this graphically or actually geometrically using the area of a trapezoid. So I need to find this y value here and this y value here. And I know this distance right here, that's the height of my trapezoid, that's 6. So remember, area equals 1/2 base 1 plus base 2, sorry my computer's a little glitchy, times h, 1/2. B1 is when I plug in a 1, so 3 times 1 minus 2 is a 1, plus 3 times 7, so 21 minus 2 is 19, times the height of 6. So I've got 1/2 times 20 times 6. This works out to also be exactly 60. So you could check the area for a linear function like this very simply using a geometric shape. Okay, so that is how we find the exact area under the curve of a function using the limit definition. Okay, so it's taking those approximations that we did last time and then taking an infinite number of those approximations essentially. And we do that whenever we add an infinite number of things together, because we don't want to actually spend the time to add an infinite number of things together, because we would never actually finish that. Instead, we take the limit as n approaches infinity and then use our limit properties to see what our areas are. Okay, as always, questions, concerns, go to Prof. Rob Bob Khan Academy, and as always, your handy dandy textbook.